Hot takes freeze faster, literally. I'm not talking about online arguments here. I mean freezing like in turning water into ice. Hot water that is close to boiling freezes faster than cold water brought to room temperature. This effect was named after a microbiologist, the late Dr. Mpemba. He discovered this phenomenon in 1962 while trying to find out if there were any advantages to using a microwave to sterilize Petri dishes, and he noticed something weird. The hot water from the microwave froze faster than the cold water he had left out to cool. This observation upended our intuitive understanding of physics. Shouldn't the cold water freeze faster? Sometimes it does. But when it comes to water at room temperature versus water that's just been boiled, the hot water wins. Hands down, or should I say nose down. Now that we've made you feel really smart by explaining something you already knew, let's make you feel stupid, because it turns out that scientists still do know why this happens. There are a few good hypotheses, though, and they all have something to do with the way water loses heat. One leading hypothesis is that as the hot water cools down, it loses heat by evaporating into a gas. Less water means less mass, which means less heat to get rid of. So the remaining liquid water can cool down faster and reach the freezing point more quickly. A study published in 2018 seemed to support this idea. It used a high-speed camera to show that the water that evaporated off the surface of the hot water was significantly hotter than the surrounding air, meaning that it carried away more energy per unit of time than the same amount of cooler water would have. But this explanation doesn't hold up in all cases. For instance, the effect seems to be stronger in deep containers than shallow ones, which makes sense if you consider that the water at the bottom of a container is unexposed to air and therefore couldn't evaporate. And there are other observations that suggest evaporation isn't the only factor. For instance, the effect also happens with very salty water, which doesn't evaporate fast enough to account for the speed of freezing. Another hypothesis is that convection plays a role. It's the process where warmer water rises and cooler water sinks, which creates currents that distribute heat throughout the water. This may lead to hotter water cooling down faster, because the hot water at the top of the container is quickly replaced by cooler water from the bottom. But this doesn't explain why the effect is stronger with deeper containers either. There is evidence for another factor at play as well. When you put a hot liquid like water into a cold environment, it can actually end up getting colder faster than the surrounding air. This is called supercooling, and it happens because pure water can remain liquid below its freezing point. But once it reaches its freezing point, it can't give up that liquid state without some help. If that help doesn't come in the form of extra jostling from convection currents, it can wait a long time before it freezes. Basically, the hot water needs a little nudge to freeze. That nudge could come from bubbles in the water, which form when the hot water is first placed in the fridge and quickly expand, creating enough jostling to kick the water into freezing mode. Or it could come from impurities like salt. Either way, this hypothesis explains why hot water can freeze faster than cold water. But again, it doesn't explain why the effect is stronger in deeper containers. And to be honest, no one has come up with a hypothesis that explains every detail of the Mpemba effect. Perhaps the reason has to do with the container itself. Maybe the material it's made of, maybe the shape, or maybe it's something else entirely. And that's why nearly 60 years later, scientists are still trying to figure this out. VE tested over 30 liquids from ethanol to milk and found that the effect isn't limited to water. Some liquids freeze faster when they're hot, but the effect varies depending on the liquid. So it's not just about water molecules bumping into each other and turning into ice. There must be something more, something we don't know. But here's the thing. Science doesn't always operate the way we think it does. We like to think it's a neat and orderly enterprise where experts make meticulous measurements, test a hypothesis, and then refine their theory based on whether or not their hypothesis was correct. But science is messy. Experiments don't always go as planned, and observations don't always fit our theories. But those unexpected observations can lead us to discover something new. They can teach us something we never would have found if we only paid attention to the question we thought we were answering. The Mpemba effect didn't turn out to be the neat little physics puzzle that scientists first thought it was. But who knows? Maybe it'll lead to a discovery that rewrites the rules. And maybe that's the real lesson here. Sometimes what looks like a setback heats up your breakthrough. Thanks for watching this episode, which was brought to you with the help of our patrons. If you'd like to help us make more videos about weird science stuff that seems too strange to be true, you can go to our support page to learn more.